Control Systems Practical Twin Rotor MIMO System Module Code ME2302. Twin Rotor MIMO System. The Twin Rotor MIMO System or TRMS is basically a prototype model of a helicopter. Aerodynamic controlling of a helicopter and TRMS are different. This is a laboratory model setup of the twin rotor MIMO system. MIMO stands for multiple input, multiple output. The twin rotor MIMO system basically the combination of a mechanical and a electronic unit. The mechanical unit of TRMS consists of two rotors. One is for main rotor and the other one is the tail rotor. Here you can see the main rotor and here there is the tail rotor. The main rotor controlled by the feedback of the pitch angle. And the tail rotor can be controlled by the feedback of the yaw angle. Here you can see the yaw axis. You can take yaw axis as the axis Z. So if you can measure the yaw angle with respect to this axis, Z axis, and this is the X axis, and you can call it as pitch axis as well, and you can measure the pitch angle regarding to this X axis. Both these rotors are connected to the free beam at its two ends, which are driven by two separate motors, the main rotor and tail rotor. And you can see here, this is the counterbalance beam which is placed here with appropriate weight that can move freely. Main rotor is producing the lifting forces upwards direction and tail rotor producing horizontal movements, making yaw angles this direction and this direction. This is the tail shield to protect the tail rotor while this is operating, and the main shield is here for protect the main rotor while it's working. Here you can see the pivot, and this is the base, the tower. Those are the main features of the twin rotor MIMO system. This is a nonlinear system with strong decoupling in between the rotors. To keep the model identification is more simple, which are two linear rotor models with two linear coupling in between. So model identification technique consists four best fit models as here. Two for main dynamic part. Here U1 to 5 pitch angle and 2 for here U2 to shy your angle, and there are two for cross coupling paths as well, U1 to shy and U2 to 5. This is the schematic block diagram of two input two output system or twin rotor MIMO system. U1 and U2 are the inputs of the system. Phi, pitch angle, and psi, yaw angle, are the outputs of the system, and those are the gains. Main pitch gain G11, cross pitch gain G12, cross yaw gain G21, main yaw gain G22. Twin rotor MIMO system consists of four best fit models, two for main dynamic part and two for cross coupling part. The main dynamic part is from U1 to 5 pitch angle. The corresponding gain is the main pitch gain G11, and U2 to psi yaw angle. The corresponding gain is main yaw gain G22, and there are two cross-coupling dynamic paths. Those are U1 to psi yaw angle. The corresponding gain is cross pitch gain G12, and U2 to psi pitch angle. The corresponding gain is cross yaw gain G21. Now we are going to start our practical. Here you can see the practical instrument of the twin rotor MIMO system. As you can see this, here this is a kind of a prototype of a helicopter. I will show you the major components of this instrument. Here you can see this is the main rotor and the blade which can rotate to both directions, and here you can see the DC motor. This is the main shield to protect the blades while it's rotating. In the other ends of this free beam, you can see the tail rotor or yaw rotor and the blades and the tail rotor shield as well, this one. Here you can see counterbalance beam and the counterbalance weight. Those beams are connected to this pivot. And here you can see this is the control unit. For this system, you can operate TRMS, twin rotor MIMO system, by pressing this start button and stop button here. So you can now have a basic idea about twin rotor MIMO. Now we are going to operate cross yaw ident. First, you have to select TRMS real-time models. Here you can see cross yaw ident, right? So this is the cross yaw ident. First of all, you have to press incremental build here, so you can see if there is any errors in that code. Then you have to connect it to the target. So the program is in the computer. You have to connect this program to this instrument. Then start the twin rotor MIMO and start real-time code. Now here you can see how pitch and yaw varies with the time. Here this is the yaw ident, so mainly you have to consider about the yaw angle with the time, but here automatically you can observe the pitch angle as well with the time. Here you can see yaw angle is trying to oscillate around the 0. Because of the control system, it always trying to oscillate around the 0, and it is keep to try it's as a sinusoidal wave according to the control system. If you put any disturbance here, you can also measure, you can see the disturbance angle, and again it is trying to maintain its yaw angle around the 0 axis here. Now the operational time has over. You can stop using this stop button. You can clearly see how pitch angle and yaw angle varies with the time. It always trying to oscillate around the 0 and trying to reach the 0 angle. Now we are going to observe how yaw angle changes with feedback values of TRMS PID yaw. Here again it is also in the TRMS real-time models. If you select TRMS real-time models here, then here you can select TRMS PID yaw. So according to this practical, you have to put different PID parameters into this box, and you have to observe how yaw angle changes with the time. So here PID parameters are set into here P parameter is 2, I parameter is 0.5, D parameter is 5. Again, as you saw earlier, first you have to click incremental build here. There is also, you can see if there is any error, you can see here. Then connect, you have to connect it to the target. Then only you can start real-time code here. Before start real-time code, you have to start your twin rotor MIMO instrument. Then connect to the target. Here you can see control signals with the time, and here you can see in this graph you can see two informations. One sinusoidal line is for simulated yaw angle for this model. Here you can see in the yellow line, this is the simulated yaw angle from this control system. The pink line represents the real-time yaw angle for this model. If you put a disturbance here, you can clearly see as it was here, and here you can see there is a disturbance, and with the time the pink line is trying to merge in with the yellow line to control this control system. So always yellow line is trying to, it means the yaw angle is trying to always merge in with the real time the simulated yellow line, simulated yaw angle. So this is for twin rotor MIMO system PID yaw. These angles depends on the PID values. What you have to do is you have to put different PID values here, and again apply PID values, then connect it to the target and start real-time code. If you do it again and again, you can observe how it's work with different PID values. Now I am going to show you a little demonstration about how both tail rotor or yaw rotor and main rotor or pitch rotor operate with the same time, and observe how control system seems with the time. Here you can see the pitch and yaw angle with the time and control signal as well. Here control signals for pitch rotor, yaw rotor control signals here in this graph, and pitch angle in this graph, yaw angles in this graph. Here you can see pink and yellow color sinusoidal lines. Yellow color sinusoidal lines represent the simulated angles, and pink color line represent the real pitch angles and yaw angles. If you put any disturbance to this beam or that shield, clearly you can see in this graph, as here, both pitch angles and yaw angles you can see here. But according to this MIMO system, you can clearly see pink line always reaching to the yellow lines and trying to merge in with yellow lines to control this system. So this is the conclusion of the control system according to these graphs.